Hello everyone, welcome to my channel. Today I'm going to present one of the important quantities in physics which is often challenging for students, and that is moment of inertia. In simple terms, moment of inertia is the resistance of a rigid body to rotating or spinning. So in linear motion, we have learned about mass and how it resists acceleration. Moment of inertia is similar, but for rotation, and it's like the rotational equivalent of mass. It depends on the shape of the body, mass distribution, and orientation of the rotational axis. As an example, consider a rotating rod about two different axes. In this example, first we rotate the rod about the axis parallel to the rod, and we experience that it is easy to rotate this way. However, if we consider the rotation axis perpendicular to the rod, we experience that this is harder to rotate this way. But why is that? Because in the left figure, the mass of the rod is distributed closer to the rotation axis. But in the second situation, the mass distributed far away from the rotation axis depends on the length of the rod. Now consider a blade of table saw rotating with a constant angular speed omega about its rotation axis. So this blade has a kinetic energy due to that rotation, but we cannot apply the familiar formula K equals 1 over 2 mv squared to the blade as a whole, because that would give us the kinetic energy only of the blade center of mass, which is 0, because the blade does not move. That's why this term will be 0. Instead, we can treat the blade and other rotating rigid bodies in general as a collection of particles with different speeds. So this blade consists of numerous particles. So we can add up the kinetic energy of all particles to find the kinetic energy of the body as a whole. For all particles will be like this: 1 over 2 m1 v1 squared for the first particle, plus 1 over 2 m2 v2 squared for the second particle, plus 1 over 2 m3 v3 squared for the third one, and so on. We can simplify this sum of kinetic energy into this form, in which mi is the mass of the ice particle and vi is its speed. But vi is not the same for all particles. Therefore, instead of v, we can substitute r omega. The total kinetic energy will be this format, and if we rearrange the quantities, we get 1 over 2 summation of mi ri squared times omega squared. Here omega is the same for all particles. The quantity in parentheses tells us how the mass of the rotating body is distributed about its axis of rotation. We call that quantity the rotational inertia or moment of inertia. And we show it by I. Stands for inertia. Remember that axis must always be specified if the value of I is to be meaningful. We may now write I equals to the summation of mi Ri squared. And the unit of I, or moment of inertia, is kilogram meter squared in SI. Now, substituting I in this kinetic energy equation, we get K is equal to 1 over 2 I omega squared. Kinetic energy of rigid body in pure rotation. This is the angular equivalent of the formula 1 over 2 m v center of mass squared. This is kinetic energy in pure translation. And as I said before, in pure rotation. Now it will be instructive to compare pure translational motion in fixed direction with pure rotation with fixed axis. So the equivalent of position will be angular position. The equivalent of velocity will be angular velocity. The equivalent of acceleration is angular acceleration. And the equivalent of mass is rotational inertia that we discuss here. And also, Newton's second law, which is given by F equals ma, in rotational motion will be torque equals I times alpha. Thank you very much to watch this video, and please follow the other videos in this channel.